Well, so in the last lecture we discussed principal curvatures, lines of curvature, and some relationship, different interesting relationship among all these invariants. So, there is another important formula called Rodrigue formula. Which relates the principal curvature with other geometric invariants of the surface. So, as usual we have a surface which is regular, and if k is the principal curvature and dui, let dui, let me write down the full statement, let dui I runs between 1 and 2 is the principal direction, is a principal direction. On a surface r equal to r of u1 u2, then following formula holds, that is, in fact then it is true from both sides. dui is a principal direction on a surface if and only if the statement is true from both sides. dn plus k dr equal to 0. In this case, this k is the principal curvature along this principal direction. If you have a normal curvature along the principal direction, then this is the principal curvature. So, in this formula k is the principal curvature. This formula is known as Rodrigue formula. So, the box formula is known as Rodrigue formula. Here k is the principal curvature along this principal direction. Here k is the principal curvature. Along dui, the principal direction. Now, in order to prove this formula, I will recall a relation that we had for a principal curvature k n. If you recall, we have proved that k n is given by b 11 plus b 12 lambda upon g 11 plus g 12 lambda, and this was also equal to b 12 plus b 22 lambda upon g 12 plus g 22 lambda. This expression we had got for the principal curvature. If you recall, while establishing this relationship, we had assumed that derivative of k n with respect to lambda is 0. So, this k n is actually the principal curvature, and the symbol you remember, lambda stands for the direction along which this curvature is considered. So, this is du 2 over du 1. Okay. Now, I will call this relation as 1, and I will exploit this relation to work out that box formula. So, first of all, let me multiply cross in the first equality. So, this will become B11 plus B12 lambda minus G11 minus G12, or you can take plus G12 lambda, okay, equal to 0. When you take the first term and the second term together, you will be getting this. On the other hand, if you take this equality k n equal to this much, then I will be getting B12 plus B22 lambda minus k n is also there, k is also there, or you can write down k over here. Okay. B22 lambda minus k times, k you can keep out, G12 plus G22 lambda equal to 0. I will look at both these expressions simultaneously. B11 we know is N1 dot R1, B12 is N2 dot R1, this will be minus N2 dot R1, or okay, keep it N1 dot R2, N1 dot R2, both are same, in fact does not matter. First of all, what I will do, I will take the term of lambda out. Okay. Let me simplify a little more, take the term of lambda together. So, B11 minus G11 into k plus the terms of lambda, this is B12 minus G12 k equal to 0. Same thing I will be doing here also simultaneously, B12 minus k times G12 and then plus B22 lambda times plus lambda times B22 minus k times G22 equal to 0. Now, I will write for B11 as N1 dot R1 and this is minus times. If I multiply throughout by minus, so this minus will not disturb me. So, if you make this minus and this plus, this minus and this plus, that is better. Same thing you do here also, minus plus minus plus. Right side is 0, so does not make any difference. So, G11 means k times R1 dot R1 and now it will become plus N1 dot R1 plus this term first. So, this is R1 dot R2 k times R1 dot R2 and this will become plus N1 dot R2 and 2 lambda equal to 0. Same thing we are doing here also. So, this is R1 k times R1 dot R2 and then plus N1 dot R2 plus lambda times R k times R2 dot R2 and then plus R N2 dot R2. lambda is also there equal to 0. I hope it is visible in the right extreme. Okay. Now, if you look at these terms of k together, now I can write down in place of lambda as du2 over du1, and then I will multiply throughout by du1. So, the equation will look like this. Am I right? Write in place of lambda du2 over du1 and then multiply throughout by du1. So, your equation will look like this. This is du1 and this is du2 equal to 0. Okay. Now, look at these terms, k times r1 du1 plus k times r2 du2. I have taken this term and this term, okay, dot r1. Is it okay? Underlined term are written like this, and then I will combine this term, that is n1 du1 and this term, plus I can also write this as n2 r1. Okay. Okay. I can write down this as n2 r dot r1. Both are same. Du2 dot r equal to 0. Plus, I am sorry, this is a plus sign. So, in short, what I have, k is common. So, this term becomes k times r I dui dot r1. Dot r1 I can write down outside, plus n I dui dot r1 equal to 0. Okay. So, this, or I can also write down k times dr. This fellow can be written as dr, and this quantity can be written as dn, and dot r1 equal to 0. Similar calculations are being done here also simultaneously, and this will lead you to k dr plus dn dot r2 equal to 0. So, what I follow from here is that this quantity in the black bracket k dr plus dn is perpendicular to vector r1, and what we follow from here is that k dr plus dn is perpendicular to r2. Is it right? Now, if I combine the two expressions, you will say that k dr plus dn is parallel to n, because it is parallel to r1 cross r2. R1 cross R2 is parallel to n, it is a unit vector. And now, if you look at it closely, this dr is perpendicular to n. Dr, everybody knows, is a tangent vector. So, dr dot n is always 0. This is tangent, this is normal, or if you want to see it as r1 du1 r2 du2 both are perpendicular to n, as well as dn dot n is 0. This is also known to us. In other words, this quantity is perpendicular to n. Also, k dr plus dn is perpendicular to n. So, a vector which is parallel to n as well as perpendicular to n has to be none other than the 0 vector. So, what you have shown in fact is so, the conclusion that we draw from the last line is that k dr plus dn is in fact 0, and this is what the Rodrigue formula says. The only thing that you need to remember that we have made use of the fact that the direction dui is a principal direction, and this is the principal curvature along the principal direction, of course. So, this is an interesting formula. Huh? Yes, this is true from both sides. It is a characterization for principal direction. Okay, in terms of the yes, converse can be proved. Converse I did not take up, but it can be done. Just go the other way around. Converse can be obtained by proceeding in the reverse direction. By proceeding in the reverse direction. So, you have to start from this box condition that this quantity is 0, and therefore, it will be perpendicular to everything r1, r2 and n, and this will give you this expression, which is the principal curvature. Okay. And the direction subsequently will be principal direction. Now, there are some interesting consequences of this formula. By making use of this formula, we can work out some other interesting formulas. For example, yes, it is the name of a mathematician. Yes. So, there is an example. This says that the following condition holds. On a regular surface, we have, I am just writing down the mathematical equation dn dot dn plus m times dn dot dr plus k times dr dot dr equal to 0. M here denotes the mean curvature. We discussed the mean curvature. The sum of the principal curvature is known as the mean curvature. Usually, it is denoted by the symbol m. So, here m is this is the only unknown quantity. So, here m is the mean curvature. So, this relationship is interesting because it relates the mean curvature and the Gaussian curvature, and we have derivatives of n and r. Okay. So, let us see how we can establish this relationship. Now, without any loss of generality, we can always consider the lines of curvature as parametric curves. So, this assumption we can always make. So, to prove this relation, assume for the sake of convenience, this can always be done. So, for convenience we always assume like this, assume that the principal or the lines of curvature, that lines of curvature are parametric curves. Yes, and that means we have done a theorem which says that if parametric curves and lines of curvature are same, then G 1 2 will be 0 as well as B 1 2 will be 0. So, this becomes available to you. Okay. And now, we can make use of the Rodrigue formula to establish this relationship. So, for u 1 curves, so since these curves are parametric curves, so for u 1 curve, for u 1 curves what will happen? du 2 will be 0. So, dn will become what? For u 1 curves, dn plus k dr will become what? Yes, it will become n 1 du 1, du 2 will be 0 plus k times r 1 du 1 equal to 0 by Rodrigue formula. And similarly, for u 2 curve, you may call it number 1. Similarly, for u 2 curve, we will be having n 2 du 2 plus k times, and let me denote this by k 1. Okay. So, that you know your principal curvature is along the u 1 curves, and this is k 2 to distinguish also r 2 du 2 equal to 0. This is number 2. Okay, now, I have to make use of these 1 and 2 to get hold of this. Now, dn will be what? The general dn, not along any parametric curves, general dn. Oh. So, dn, now dn equal to now, can you, if I look at 1, look at what 1 gives me, let me further simplify 1. N 1 plus k 1 r 1 into du 1 is 0, and since you are moving along u 1 curves, so du 1 is not 0. So, this fellow is 0. So, from here I will be getting n 1 equal to minus times k 1 into r 1. You may call it number 3. Similarly, from 2, what you will be getting? You will be getting n 2 equal to, this will be 0 minus k 2 r 2. So, this is number 4. So, we will be using 3 and 4 rather than 1 and 2. So, now look at what will be dn. dn by definition is n 1 du 1 plus n 2 du 2. Okay. and n 1 from number 3 is minus k 1 r 1 into d u 1 is there, plus n 2 is minus k 2 r 2 into d u 2. Okay, this is d n, and you have to see what is d r, you may call it number 5. So, d n, this value is number 5. Now, look at d r. d r is r 1 d u 1 plus r 2 d u 2. So, k times, if you need k also, so this will be k, here it will be k, this is number 6. Okay. Now, by Rhodic formula, no, I do not need to multiply k, leave it. Okay. So, first I will see what is d n from 5 and 6. It will be 0. We can directly put it equal to 0, but what I will be interested in, I am interested in d n plus k 1 d r. Okay. So, d 1 plus k d r you can compute from here, in fact this will be 0. K 1 d r, not k d r, I am just looking for, if you want I can compute it. So, d n is there, so this is here minus k 1 r 1 d u 1 minus k 2 r 2 d u 2 plus k 1 r 1 d u 1 plus k 1 r 2 d u 2. So, k 1 r 1 d u 1 and k 1 r 1 d u 1 are cancelled out. What you get, it is not 0 in fact, it will be 0 only if this k 1 is not k, it is k. So, this it becomes k 1 minus k 2 into r 2 d u 2. This is number 7, and d n plus k 2 d r also we need to compute. So, d n also from this relation I can find out d n plus k 2 d r. So, that will be minus k 1 r 1 into d u 1 minus k 2 r 2 d u 2 plus k 2 r 1 d u 1 plus k 2 r 2 d u 2, and this time k 2 r 2 term will be cancelled out, and this will give you k 2 minus k 1 into r 1 d u 1. This is number 8. Yes, yes, yes. We can multiply them. Okay, exactly. So, now let us find out the dot product of these two. So, d n plus k 1 d r dot, these are vectors you know. So, d n plus k 2 d r their expressions are available in 7 and 8. So, you can see, you can directly see that the right side will be 0 because of R 1 dot R 2. R 1 dot R 2 are it is G 1 2. R 1 dot R 2 is G 1 2 and G 1 2 is 0 because their ortho parametric curves are lines of curvature, and lines of curvature are always orthogonal. So, the right side is 0 and this is 0 by 7 and 8. By 7 and 8, and the assumption that G 1 2 and B 1 2 are 0. Now, if I simplify the left hand side, it will give me d n dot d n plus, if you consider the product of this and this and this and this, you will be getting k 1 plus k 2 into d n dot d r. And when you will take this and this term together, it will give you k 1 k 2 is equal into d r dot d r. And the right side we have already seen is 0. Now, this is the sum of principal curvature and this is the product of the principal curvature. Sum we call as m, the mean curvature, d n dot d n plus m times d n dot d r plus, let me call it k. K means the Gaussian curvature, or you, if you want to call it G, you may call it G. I do not know which symbol I use for Gaussian curvature. K, okay. Okay, so you may call it K. So, dr dot dr equal to 0. So, this establishes yet another important relationship among some known curvature measures like Gaussian curvature and mean curvature and the invariants of the surface. Okay, and this can be obtained just using the Rodrigue formula. All yes, that is right. This was very important to us. All right. Now, the next thing, before doing something else, let me look at some problems. The lines of curvature and principal curvature, etc., for some known surfaces. So, for the surface, so this is one of the exercises given in the lecture notes. For the surface, r equal to u v u square plus v square, find the lines of curvature and principal curvature. Find the lines of curvature and principal curvatures. Okay, for principal curvatures, we know that we have a differential equation that represents the principal curvatures, the lines of curvature and principal direction, sorry. So, for lines of curvature, we will look at that differential equation, okay, that can be written in the form of a determinant. If you remember, that is in fact, I may write down here du 2 square minus du 1 du 2 and du 1 square equal to 0. These rows are G 1 1, G 1 2, G 2 2, B 1 1, B 1 2, and B22. So, first we work out the differential equation that describes the lines of curvature. So, what you need to do is you need to find out the Gij's and the Bij's. So, for the given surface r equal to u v u square plus v square, the parameters of the surface are u and v. Okay, so, r 1 means derivative with respect to u. So, that will be 1 0 to u, r 2 will be 0 1 and 2 v, and from here I can compute n also you can compute from here, and the cross product will give you minus 2 u and then minus 2 v, and this will give me 1, and you should divide by its magnitude. So, this is 1 plus 4 u square plus 4 v square. This is the unit normal to the surface, and this follows from here. G11 immediately it will be 1 plus 4 u square, G22 equal to 1 plus 4 v square, and G12 is 4 u v. These are the Gij's on the given surface. Now, Bij's, so first starting from B11, it is n dot R11. So, this is R11 also I must compute. We forget to compute R11 is constant 0 0 2. R22 similarly is 0 0 2, and R12 is simply 0 0 0. These are Rij's. Now, I can work out Bij's. So, starting from B11, this is n dot R11. N is here, R11 is here. So, the dot product of these two vectors you can just see it will be 2 upon under root 1 plus 4 u square plus 4 v square. Directly you just see and you get it. The B22 is how much? N dot R22. So, this will be same 2 upon under root same quantity. B12 is n dot R12, that will be 0 because R12 is 0. So, this B12 is 0. Okay. B12 is 0 because R12 is 0. You are differentiating with respect to V, that is right. So, we have got all the elements of the determinant. I can write down the differential equation for the lines of curvature. So, the differential equation for the lines of curvature, the differential equation for the lines of curvature is therefore first let me write down in the form of determinant. du2 means dv square, and here minus du dv, and this is du square. Okay. G11 is where? Here, 1 plus 4 u square without a square root. 1 plus 4 u square, and this fellow is 4 u v, and again 1 plus 4 v square, and in the last row we have 2 upon under root this quantity B12 is 0 and B22 is once again 2 upon square root 1 plus 4 u square per 4 v square. Okay, so, this equal to 0 is the differential equation. Okay. You can rewrite this differential equation in a natural manner, and the solution of this differential equation will give you the lines of curvature. Lines of curvature is not a single curve, it is a family of curves. So, family of curve is represented by a differential equation. Okay. So, this differential equation represent, and what will you be doing for principal curvatures? Yes, you have to write down the quadratic equation for the normal curvature. Okay. The roots of this quadratic equation will be the principal curvatures. So, that was, if you remember, that was what? K n square minus B I into K n plus B upon G equal to 0. Now, most of the things are readily available to you, only BII you have to work out. How would you work out BII? For example, this BII means B11 plus B22. When I say BII, I mean B11 plus B22. Okay. So, for example, if you want to find out B11 first, so B11 I will work out like this: G1k into BK1, and G1k will be from 1 to 2. So, there is k is a dummy index. So, G11 into B11 plus G12 into B12. B11 and B12 we have already computed here. So, these values are readily available to us. The upper Gij's are to be seen what they are. So, in order to find G's upper ij's, for example, G11, it will is what? It is G22 upon G. So, G22 is here with me. Where it is? Where it is? G22 here, this 1 plus 4 v square upon, now you multiply these two, 1 plus 4 u square into 1 plus 4 v square minus 4 u v. This is the value of G upper 11. Square, I am sorry, square, you are right. So, 16 u square v square. You can see this will be 16 u square v square, you can simplify. So, this simplification I will not be doing here. Okay. Similarly, you can compute G22, G12, all you need G12, do not compute anything else. So, G12 you can compute. So, this is minus G12 upon the same thing, and this will give you the value of B11. Similarly, you have to compute the value of B22. So, there is a little bit of computation and nothing technical. Okay. So, you will be able to write down this quadratic equation, and from here you can see what are its root, they will be the principal curvature, and this way This is just in fact, in order to show you how to compute these quantities. I can ask you find the lines of curvature and principal curvature on surface of revolution, on the surface z equal to f x y, things like this. So, all these computation now you can do. I will stop for 5 minutes and then we will